Hi guys, so today we're going to take a look at question 8 of the 2017 exam, paper 1. When a loan of €P is repaid in equal repayments of amount A at the end of each of T equal periods of time, i.e., months or years or weeks, where I is the periodic compound interest rate expressed as a decimal, the formula below can be used to find the amount of each repayment. A equals P times P by I by 1 plus I to the power of T, all over 1 plus I to the T minus 1. So we want to show how this formula is derived. Where does this formula come from? And to do so, we may use the formula for the sum of a finite geometric series, which should be a pretty major hint. Okay, so we're looking for a loan of P to be repaid. Okay, so a loan P repaid in, not repaid in equal repayments of A. At the end of each time period. So we've got to consider how much is €1 worth to the bank in, after 5 time periods. So let's say they give us P euro. Well, after 1 time period, we give them A, but because of interest, that €1 is not worth €1 to them. It's not worth the same amount as, let's say €1 that we borrowed. Because interest has made money less valuable. So this is only worth A over 1 plus I. So if interest was 10%, this would only be worth A over 1.1 to them. And then the second repayment, again, we're giving them A, but that's not worth A to them. It's worth 1 plus the interest rate squared. So this is what this repayment of A is worth to them. And then so on and so forth for all the repayments. A over 1 plus I, and I believe there were T payments. So this is our formula here. This is the formula of what we are repaying them. So at the end, they want to have gotten P value back. So €P in value back from us, which is not necessarily €P because money is it's less valuable over time. Okay, so now we've constructed this geometric sequence where the first term, and if you couldn't see that it was a geometric sequence, the fact that there's a sum of a finite geometric sequence series should be a big hint where you should be, where is there a geometric series hidden here? Okay, so a geometric series is of the form, A plus AR plus AR squared plus blah, blah, blah. So there's a starting term and then there's a common factor. So our starting term is clearly A over 1 plus I, and then each successive term is multiplied. So starting term, each successive term is multiplied by a factor of 1 over 1 plus I. There's another 1 plus I, a factor of 1 plus I, on each successive denominator. So on the first denominator, there's 1 power. On the second, there's 2. On the teeth, there's t powers. Okay, so we have this formula a plus ar plus and so on and so forth plus ar to the t minus 1. Not to the t, because this last term, a over 1 plus I to the t, it only has t minus 1 more copies of 1 over 1 plus I than the first term, because the first term already has 1 on the bottom, and this has t, so it has t minus 1 more copies of 1 over 1 plus I. Okay, and so now if we look at the formula for a geometric series, so S n minus 1 is equal to a times 1 minus the ratio to the power of n. So the starting value by 1 minus the ratio to the power of n, all over 1 minus the ratio. Okay, so let's fill in our values of a and r. So this sum, which is s of n minus 1, this sum, which is just p, how much we're paying back, equals a, which is big A over 1 plus I, by 1 minus the ratio to the power of the number of terms, 1 minus 1 over 1 plus I, to the number of terms, there are t terms, all over 1 minus the ratio, 1 minus 1 over 1 plus I. Okay, and now we want to simplify this. So if we multiply the top and the bottom by 1 plus I to get rid of this ugly thing here, and it will actually also get rid of this thing here. We don't like having fractions within fractions, so we'll try and get rid of that. So if we multiply top and bottom by 1 plus I, we'll get p equals a by 1 minus 1 over 1 plus I to the power of t, all over 1 plus I minus 1, because we'll get a 1 plus I term from this, and then multiplying this by 1 plus I will just give us 1. Okay, so then if we continue to expand this out, we'll get an a equals 1, we get an a times 1 minus 1 over 1 plus I to the power of t. So this term is just 1 over t, 1 to the power of t by 1 plus I to the power of t, and 1 to the power of t is just 1, of course, all over I. And again, to get rid of the fractions within fractions, we're going to multiply the top and the bottom by 1 plus I to the power of t. So we're going to get p equals a times 1 plus I to the power of t minus 1, all over I by 1 plus I to the power of t. Okay, and now we're most of the way there. I actually don't even know what it is we're trying to show. I just know that we're trying to find an expression for a. So then if we try and isolate a here, we'll multiply both sides by this denominator, you know, how we would typically work with a fraction. So we get p by I times 1 plus I to the power of t will equal a by 1 plus I to the power of t minus 1. And now we'll divide both sides by this term, and we get a equals p times I times 1 plus I to the power of t all over 1 plus I to the power of t minus 1. And hey, that's actually what we're looking for. So we've shown what we're looking for. Now, this is the kind of formula that this is the kind of proof that a lot of teachers will get you to just learn off. And I think it's better to just understand how paying a loan back works in terms of returning the value to the bank. So this section here. And then just using our knowledge of a geometric sum, and then just manipulating this expression, this big expression here, to try and express a in terms of everything else. So trying to isolate a. And there's a couple tricks, you know, multiplying by the 1 plus I over 1 plus I, but they're not even really tricks. Like, I mean, that's just what you would do standardly. You know, if you were trying to isolate the a, you know, you would try to get rid of fractions on the numerator and the denominator, because we don't like working with those. So I think your headspace is much better off trying to understand concepts rather than rote learning proofs. But it's really not that bad. Now on to part B. Alex has a credit card debt of €5,000. One method of clearing this debt is to make a fixed repayment at the end of each month. The amount of this repayment is 2.5% of the original debt. What is this fixed monthly repayment required to pay the debt? Okay, so seems very straightforward. The debt is 5,000, and the monthly repayment is 2.5% of the debt. So his monthly repayment to pay off this debt is just 2.5% of 5,000, or 0.025 by 5,000, which is €125. Very nice first part of B. Now on to part 2 of B. The annual percentage rate, the APR, charged on a debt by the credit card company is 21.75%, fixed for the term of the debt. Find as a percentage, correct to 3 significant figures, the monthly interest rate that is equivalent to an APR of 21.75%. Okay, so we have a yearly interest rate, yearly compound interest rate of 21.75%. And so what is the monthly? So we're looking for the monthly. Well, we know that let's say it's I, and we'll try and figure out what I is. We know that this monthly rate will compound over the year to give us the yearly rate. So 12 months in the year. This will give us the yearly rate 1 plus 21.75%, 0.2175. So now we have this equation which we can then solve. 1.I to the 12 equals 1.2175. And now we just take each side to the power 1/12. So we get 1 plus I equals the right-hand side, 1.2175, to the power of 1/12. And then we bring over the 1, so I equals 1.2175 to the power of 1/12 minus 1 equals 0.016535, or to three significant figures, 1.65%. So a monthly interest rate of 1.65% is equivalent to a yearly interest rate of 21.75%. Now on to part 3. Assume Alex pays the fixed monthly repayment of A, which we know is 125, each month and does not have any further transactions on the card. So this is the only thing happening. We don't have to worry about anything else. Complete the table below to show how the balance of the debt of 5,000 is reducing each month for the first 3 months, assuming an APR of 21.75% charged and compounded monthly. So the interest rate we've been working with. Okay, so we know that the fixed monthly repayment is just, so let's call that the fixed monthly repayment, the FMP, or A, equals 125. We know that, so we can just fill these in. And then calculate the interest. So there's this monthly interest of 1.65%. Okay, so over the first month, that debt of 5,000 increases by 1.65% because he pays at the end of the month. Okay, so the 5,000 becomes 5,000 plus 1.65%, or 5,000 by 1.0165 equals 5,082.5, or 5,082.50. So the interest has increased by, the interest has brought it up by 82.50. Okay, and so it went up to 5,082.50, and then it goes down by 125. So the net decrease is only 42.50, and so now the new balance, 5,000 minus this, is 49.57.50, which is kind of really unfortunate. Only a third of the money he put in, approximately, went into actually paying off the debt. So it's not very good for Alex. So let's continue this now. So the current is 4,957.50. So again, it increases by 1.65%. So 4,957.50 by, well, we can actually just multiply it by 0.0165 to just get the interest equals 81.80. So the interest now is 81.80, and so the previous balance, well, then now it's reduced by 125 minus 81.80, which is 43.20. And so now the 4,957.50 is reduced by 43.20. So now it's 4,914.20. Okay, and now over the next month, that 4,914.20 increases by 1.65%. So let's calculate that interest. By 0.0165 equals €81.08. So the interest here is 81.8. So now the balance decreases by 43.92. And so the new balance, so 4,914.20 minus the 43.92 is 4,870.28. So this is how the balance of the debt reduces over the first 3 months. And not looking so good for Alex. Now on to part 4. Using the formula you derived on the previous page or otherwise, find how long it would take. How long will it take to pay off a credit card debt of $5,000 using the repayment method outlined in the beginning of part B? So the repayment method we've been talking about. Give your answer in months correct to the nearest month. Okay, so the formula that we derived on the previous page was A equals P times I times 1 plus I to the T over 1 plus I to the T minus 1. So A equals P times I times 1 plus I to the T all over 1 plus I to the T minus 1. Okay, and we have A, it's 125. We have P, it's 5,000. And we have I, the interest rate, it is 0.0165. And all we need to solve is, well, we need to solve for T. So if we plug these into our formula, 125 equals 5,000 by our interest rate, 0.0165, times 1 plus our interest rate, so 1.0165 to the power of T, all over 1.0165 to the power of T minus 1. And now we need to solve for T. So we first divide by 5,000, and we get, if we divide by these two constants here, we get 125 over 5,000 by 0.0165, which is 50 over 33. And then this equals just our 1.0165 to the power of T over 1.0165 to the power of T minus 1. Okay, so now how do we solve something like this? Okay, well first we want to get rid of this fraction, so we're going to multiply both sides by 1.0165 to the power of T. So we get, actually, you know what, we're going to cross multiply. So we're going to multiply here and here. Or, yeah. To technically this way. Okay, so we'll get 50 by 1.0165 to the t minus 50 equals 33 by 1.0165 to the t. Okay, so then if we bring the minus 50 over and then bring this 33 1.0165 to the power of t over, we'll end up with 17 by 1.0165 to the power of t equals 50. So 50 minus 33 by this term here, 1.0165 to the power of t. So then divide by 17. So we get 1.0165 to the power t equals 50 over 17. And so this expression is equivalent to the logarithm log of 1.0165 50 over 17 equals t equals 65.92 or 66 months. So it will take 66 months to pay off this loan, which doesn't seem very good. Oh, and just the reason that this equation, how we jump from here to here, well, this is just the definition of the log. So this first equation here, 1.0165 to the power of t equals 50 over 17, this is a question, 1.0165 to the power of what equals 50 over 17. And so then the answer to that is this logarithm here. That's how we define the logarithm. I've talked about this before. I have a separate video on this if you want to look at it, but essentially this is how we define the logarithm. Now on to part 5. Alex decides to borrow $5,000 from the local credit union to pay off this credit card debt of $5,000. Seems like a good idea. This credit card debt looks horrible. The APR charge for the credit union loan is 8.5% fixed for the term of the loan. The loan is to be repaid in equal weekly repayments at the end of each week for 156 weeks. Find the amount of each weekly repayment. So we're going to be using our formula A equals P, the amount he borrows, times I, the interest rate, times 1 plus I to the power of t, the length of the loan, all over 1 plus I to the power of t minus 1. Okay, so we know that P is 5,000, how much he borrowed. And we know that T is 156 weeks. But what is I? Well, calculating what I is very much similar to what we did in part 2 of this question. We're just looking for I, so 1 plus I, this interest rate, when this compounds 52 times, so over the year, it will give us our yearly interest rate of 1.085, an interest rate of 8.5%, which they've given us here. And now we just solve for I the same way we did earlier. We just 1 plus I equals 1.085 to the power of 1 over 52, and then minus 1. to get I by itself. So I equals 0.00157. Okay, and now we can plug this into our formula to get A. So A equals P 5,000 times 0.00157 times 1 plus I, so 1.00157 to the power of 156 weeks, 156, all over 1.00157 to the power of 156 minus 1 equals 36 euro and 16 cent. So that's the amount of his weekly repayment with this method. So how much will Alex save by paying off the credit card debt using the loan from the credit union instead of paying the fixed repayment? By how much is this method, this credit union method, better than the original method? Essentially the question. So in method 1, the original method, just paying off the credit card, month by month, he pays 125 euro for, we calculated, he would have to pay that for 66 months, which is 125 by 66, 8,250. So we'd have to pay 8,250 with this method. But with the second method, by taking a loan from the credit union and paying off the credit card and then repaying the credit union, he has to pay 36 euro and 16 cent for 156 weeks. So 36 euro and 16 cent by 156 is 5,640 euro and 96 cent. So this is a way better plan. In the first one, he's getting 5,000, he's paying back 8,250. In the second method, he's getting 5,000 and he's paying back 5,640. So yeah, he's going to pay back more, which you can expect, but it's not that much more. So how much would he save? Well, he would have had to pay 8,250, and he ends up having to only pay 5,640.96, which is a difference of 2,609 euro and 4 cent. So, well worth it. And another bonus, he finishes like 2.5 years earlier, which I'm not sure how important that is to him, but if I were Alex, I'd want to get out of the debt as soon as possible. So, definitely a much better method.